Good evening, guys. My name is Engineer Leo Adekunle, and today I will be explaining our last calculation on simply supported slab. Please don't forget the assignment I asked you to do on this column, and likewise, you will need all these ones for your understanding. Now, as I told you, I will explain about slab and other things before in the last note, so I will just go straight to the calculation. Please, this new note that I'll be sending will be the one that you will use, and I've also included some of the tables that you might need in your BS 8110. So as I explained the other time, I said there are some things that you need to do. You calculate the suitable depth, then you go to the main and secondary reinforcement, and likewise you do the critical shear stress calculation, and you check for your detailing requirement, the minimum percentage of reinforcement, maybe 0.14, depending on what you are using, or 13 percentage of BH and the rest. So I would like to make it brief, so please read your notes and follow as I explain. Now, supposing we are given a slab, that this slab it has an imposed load of 4 kN per meter square. Please note that when they say 4 kN per meter square for your imposed load, most of the time there's a table that you use to check that. You consult your designer manual. Depending on the building you are trying to erect, you check for the appropriate value. I think for residential it's around 2.5 or so. So it varies. Each one has its own. I might send you a copy of some of the imposed load. So but please remind me in the next lecture so that I will send you that. Now let's go to the depth of the slab. I said you calculate the minimum depth, which is the span over basic ratio times the modification factor. Now what you just need to do is you look at as I explained the other time, you look at the shortest among the two, maybe center to center of this, or the effective depth plus in to in. Then you use it. But for this particular one, I just go straight to my calculation. Now, the first thing you do is you can assume maybe 1.4 for multiplication factor, so that you know what you can use that to start your calculation. But please, that is not the final one. You just want to use it so that you know what area or what range your effective depth will be. Now, if after doing this, I have 152 mm in my calculation, then the cover size for this particular one, I said let my cover be 25 mm and my bar size is 10 mm. So mind you, I have 152 mm for my effective depth here, minimum effective depth. Now what I will now need to do is, this one will be it won't be easy to measure, so I increase it to the nearest 5 mm size, which is a 155 mm. So I will calculate my H, which is D plus diameter of bar plus 2 and cover. Note this one, there's no link like the other one we did when we were calculating for column. For this one, it's a slab. You just have your main reinforcement bar, half of it, and the cover to remove from it. So now we have our H, our overall depth, which is H, that is from here to here is H. So which is 185 mm. So we go straight to the loading. Now in the loading, you were told that we have imposed load of 4 kN per meter square, and we have there's no dead load given. So what you just do is, once there's no dead load given, the weight of the concrete will be your dead load that you will use for your calculation. Now self weight of the slab, that's the depth multiplied by the self weight of concrete, which is 24 kN per meter cube. If you multiply that one, you have 4.44. Please take note, lest I forget. Most of you always make mistake in your calculation. When you are working with kilonewton per meter cube, you have to make sure you convert the depth to millimeter to meter to radar. So that is why I have this one. One of these meter will cancel this. I'm having it in per meter square. Now you have your imposed load, which was given, as I explained the other time, depending on the structure you are dealing with. For this one, I have 4 here, so that's why I'm having 4 here. Now, after calculating I know my dead load, I know my imposed load. Now I'll calculate my ultimate load, which is equal to I apply my my factor of safety. So for this particular one, I have 1.4. What's wrong with my notes? Okay, sorry. I have it here 1.4 GK plus 1.6 QK times width of slab times span. Why am I multiplying with the width of slab? Because it's uniformly distributed. So I multiply with this one of the width, then that's multiplied by the span. Now this span is 4.25 as we have said. If I do this calculation, I have this. This is just my ultimate load, that is the maximum load that structure can carry. Now I will now calculate my design moment, which we will need for our area of reinforcement calculation. Now for that, I will use, if you notice, I have multiplied with a span here, a span length already. So for this particular one now, I will be using WL over 8 as against the WL square over 8 that we always use in class. Why I'm doing that is because I've multiplied, I'm trying to use this value here. If I'm not using this value, I'll just take it, maybe whatever value, I'll just take it directly WL square over 8. But because I'm using this value and I'm multiplied with a span here, that is why I'm using just WL. A single L has gone already, so I'm just left with one L. So I'm using WL over 8. If you do your multiplication, you have 28.5 kilonewton meter. Now, I explained to you that is just our maximum moment. Now let us look at the maximum and the ultimate moment. We have to check whether the moment you calculated is not up to the ultimate moment. If it is, then we have to introduce compression reinforcement. So I told you that ultimate moment is equal to 0.156 FCU BD square. If you do the calculation, you have 131.2 kilonewton meter. Now, if you compare these two values, 25.8 and 131.2 kilonewton meter, you realize that this one is far lesser than this. That means there is no need for compression reinforcement. So I just go straight to my steel calculation. Now, how do I go about that? I calculate my K value, which is equal to M over BD square FCU. If you do that one correctly, you have 0.0339. Now, you now calculate your Z value. Please, this one is, I think it's page 26 of your BS 8110. This formula is there, so you can always look at it and confirm. If you substitute the value of this K, substitute here, you have this. Now, whatever I have here, I must check, is this value less than or equal to 0.95D? As I've told you, the maximum value that your Z value can be is 0.95D. So for this particular one now, I will check. I have I think I have a value of 147 mm. That is whatever I calculate here, if it is less than 0.95D, then I use that value. But if it is greater than 0.95D, I will use 0.95D as my final Z value. So once you get your Z value, you calculate your AS. For this one, I have your M over 0.87 times FYZ. So if you do the calculation, you have 446 millimeters square width of slab. Now, looking at this one, this one talks about the spacing and the bar size. Now, I have 446 here. If you look at it, and I said the other time, I said I'm using what size of reinforcement? I said I'm using 10 mm. So under 10 mm bar, we look at it. I have 449. I cannot use this because it's too near to this 446. So I take the next one, which is 523. So I'm taking 523 as my AS here, and that's 523. That's 150 mm center to center spacing. You can see the spacing here. So I just select that. You say provide 10 mm diameter bar space at 150 mm, and if you are going to write it down, you can say H10 at 150 centers. And the AS you are providing, this is the AS provided now. This normal AS, the AS you are providing is this. So we now go for the actual multiplication factor. Now for this multiplication factor, there's a table 310 in your BS 8110. We are going to use this equation 8 here. This, in some textbooks you will see something like 5 over 7 or 5 over 8, but I'm limiting myself to what is written in what is recommended in BS 8110. So if you calculate 2 over 3 Fy AS required all over AS provided. If you do the calculation, now this your beta B is you can just use 1 for it. Always use 1 for it for now. That's for redistribution. You can read more in your BS 110 on that. I won't be going to that, but I think once it's provided, or even if it is not provided, just use 1 for it for now. So if you do the calculation, you have 263.98 for your design service stress. Now I go to my modification factor, because I will use this design service stress to calculate my modification factor. Now the formula is also there for your modification factor, which is 0.55 plus 477 minus Fs. If you put the value correctly, is the formula also here. You have to check whether it's less than or equal to, it has to be less than or equal to 2. So if you do your calculation, for me, I have 1.397. So what I'm going to do is that this value 1.397, I'm going to use it. That's my new modification factor. I will now use it just like the way I started. I will check whether it's going to meet up with my minimum reinforcement, like I did in the beginning of the calculation. If you can remember here, like I did here, that time we just said let us assume this, but this time around we are doing the actual calculation and based on what we have. Now my minimum is 152 mm. It's still almost the same thing, and so since it is less than the assumed, I can say my D is equals to 155 mm is okay. But if this value is less than the initial, that is, if whatever you are having here, if it is less than what you have recommended, if it is if it is greater than what you have provided earlier on, we have to increase the depth, so that we have to increase the depth and redo the calculation again. And another means is another thing is to increase the AS you are providing to. It will also help you. Let me say a short form or a shortcut. Instead of doing calculation over and over again, you can just increase your AS provided or increase your bar size. AS provided will increase, then you are good to go. Now you are going to look at your minimum area of reinforcement. Minimum area, please don't forget. AS minimum is 0.13% of BH. This is the minimum area of reinforcement that is needed. This one is you look at this. Since this value is less than the AS we calculated the right time, is less than this value of AS we calculated, the value of AS is less than this, then that means we are okay. This is the minimum area of reinforcement that is needed for this structure. So we go to this secondary reinforcement. Since we have already calculated the minimum AS, and we just use this minimum for our secondary reinforcement. Mind you, I told you the other time that there's no need for proportional reinforcement, so we just provide this for it, the minimum steel area needed for the secondary or the distributed bar. So you can look at the spacing at 200 mm spacing. We are good with that. So we calculate our shear reinforcement. Now the shear reinforcement, the way it is, you can see the way it is. I think I explained this diagram for you in class the last time. So you just look at your V, which is 20. Sorry, for this one, I think our V, I think I calculated it, 53.62. That's the total value of W. So my W over 2, because it's uniformly distributed, so they carry the same load. So if I divide that, W over 2 will give me 26.8, which is my V. That's my shear force, maximum shear force. There's no support that can carry more than that particular load for now. So my V will now be equal to my design shear stress will be 26.8 times 10 raised to the power of 3 divided by BD. Please don't forget that your B, because we are dealing with slab, the B is always 1 meter, designed to 1 meter strip. So if you do the calculation, you have 0.17 Newton per mm square. Now we go and do so we assume that 50% of our main steel is coated at the support. So if we look at 50% of it, 50% of 523 is 262. This 262 is what we're going to use to do our AS. Now, under AS or BD, we have a value here. This design concrete shear stress. the table for it is still in your BS8110, but I extracted. Let me say I try to cut it out for you so that you will not be going over and over. But you can just open your BS8110 and verify. So you based on this, you look at, okay, my my diameter of effective depth is around 155. You have to interpolate, and this 100 years over this over BD is around 0.169. So it's between this range. You interpolate, it's around this range. What you're looking for is around this range here. So when you interpolate, you get a value. For me, I have 0.4268. So because this one is under FC equals to 25 Newton per mm square, I'm trying to bring it back to 35 Newton per mm square, because that's what I'm using here. So 35 divided by this 25 raised to power 1 over 3, then multiply by what I have, will give me this 0.48. So this particular 0.48, we check, is it lesser than what we calculated here, 0.17? Because you see higher than, sorry, I say higher than or lesser than. If this one is lesser than this, then there's no need for shear reinforcement. But when it is higher, then there will be need for shear reinforcement. Okay, that table, I didn't, let me see that table, maybe I have it in the notes. Okay, yeah, this place, you can see this place. When V is less than VC, none is required. But when you can see the requirement here, so you can always follow this when you have different condition. So let me continue where I stop. I stop here. Now, so I said, since the our V is less than VC, there is no need for compression for shear reinforcement. So we go to our detailing. This is the detailing. This 200 okay, this is the detailing. 23 numbers of H08 200 bar. That's the number of bar that will span through this space, because by the time you divide 200 divided by 4,250 something, you should have around 23 numbers that will be able to cover this area. Now for this anchorage here, for this your bar detailing, you can see there's a provision for that. Is the distance and the angle is around 10. This around 10 degree also, but sorry, I mean 10 mm from here, and the way it's curved, that's the detailing of it. The 100 bar runs through, 100% bar runs through here like that, and this is your effective depth that you have calculated. So you can see how long this your reinforcement should go through. And in that I think there's a note I wrote, there's something I drew on this in this place. Yes, in this place you will see this place. I've made the calculate, and let me say reducing this the length for each of those distribution bar. This for your support, this for your span. So you can always go through that. I don't want my video to exceed 20 minutes, so I will try and round up, so that once you just go through this and check for your spacing, the spacing of the bar. You can always read this. There's no big deal about it. I talk about the crack width. Since the slab depth is less than 200 millimeter, we don't need to bother ourselves with the crack. It will cover for the it is within the permissible crack width of 4.3 millimeter. Now the class task, I want you to do this one. As you all know, you have your group A to J. So each group will take their own. You provide me with the AS main, you do the calculation for the AS main, AS provided, your FX, your multiplication factor. Then you tell me, do you need shear reinforcement, yes or no? And likewise, you make sure you do all the calculation for your moment, your K, your Z, everything. Do it. I will be collecting that on Wednesday. Yes, I'll be collecting that on Wednesday. And if there's any question you need to ask, just you can always send it to me on WhatsApp through the group, or even personally. I think I should be able to answer you. I wish you a wonderful night rest. Have a lovely day. Bye.